So, like Monica said, my name is Bill. I'm working in CCS. I just became a PDRA last year, and we did just recently move to IES, but my PhD was already in the department. It's kind of flip-flopped. And we'll talk about the organization here in a little bit. But I've been in Edinburgh for about 6.5 years now, and I'm hoping to talk today about what my PhD project was, and then what that has turned into what I'm working on now. But I also would like to do a little bit less technical parts of the talk and talk more about kind of lessons learned for people who are still PhDs. So, in theory this works? Maybe? No? Okay. So it's always difficult to understand what everybody's background is in regards to if they know what CCS is or not. So if you do know what CCS is, you can tune this out for about the next 2 or 3 slides. But what I'm calling this are the obligatory why CCS slides, which everybody has to do at the very beginning. So if you start with like a super high level statement, like climate change is primarily caused by anthropogenic generation of greenhouse gas emissions. So if you break down that whole sentence, anthropogenic means us, generation means we create CO2, greenhouse gas emissions mean gases that go into the atmosphere. That is almost wholly done by the generation of CO2, which almost primarily becomes from burning things. So if you look at how a combustion reaction works, you have to have fuel, an oxidant, and you make a product gas. We don't care about any of that. We just want the heat to, do things. But fundamentally, if you look at what each of these carbon capture technologies are, they address any of these 3 streams. So in pre-combustion capture, you're basically pre-processing the fuel. And oxy-fuel, you are basically pre-processing the oxidant. And then the one that I kind of specialize in post-combustion, you are processing the product gas. So in general, carbon capture is just 3 different technologies that try and address each of these 3 process streams. Basically, once the CO2 is processed out of any of these 3 streams, it then gets compressed and stored into geological formations. Okay, so since we are in the Institute of Energy Systems, we need to kind of think about how a low-carbon energy system works and what are the desirable traits for carbon capture within that low-carbon world. So the first one is that you're reusing infrastructure and expertise. We've been really good at burning things for the past 150 years. It's been since the Industrial Revolution. To completely throw out all of that expertise and infrastructure seems a bit wasteful and a bit expensive. The other thing is that it can be used on medium to long-term timescales. So depending on who you ask and what projections of energy use you have, you probably have somewhere between 80 and 500 years worth of storage that we know of for CO2. So this can be kind of a transitional technology towards magic worlds of no carbon electricity. The other really nice thing is that you get large power outputs from small footprints. Building a gas plant is a lot cheaper than building the 700 wind turbines that you would need to be the equivalent of the gas plant. And then the CCS plant on the back of that is kind of a low cost relative. And the footprint's a lot smaller. You can do this in a couple hundred square meters rather than in the square miles that you're going to need to get it out of renewables. This is also one of the few solutions that exists to reduce emissions from commodities. So we talk a lot about energy, and we talk a lot about electricity, but we never talk a lot about stuff. So you need steel and you need cement, and those things make CO2, and one of the only technologies to reduce that is carbon capture. And then you also get this lovely stream of compressed high purity gas that you can use to do things. So what we use it to do now is we use it to push more oil out of the ground. That's called enhanced oil recovery, which isn't really great environmentally, but in theory we will be doing more things with that stream in the future. And it's also retrofittable on existing assets. That's specifically the technology that I talk about. So if you already have a gas plant and you say, oh, well, now I want to do low carbon things, you don't have to bulldoze the gas plant and make another one. Okay, so that's great, and then you can never really get through any kind of technology option without talking about how much it costs or how it costs compared to other things. So in terms of the different types of carbon capture technology, this pre-combustion, oxy-fuel, and post-combustion, they all wash out about the same in terms of cost of levelized electricity. So they have various technical benefits, but in terms of cost, they're all about the same. And that cost is somewhere between onshore and offshore wind, depending on what economic model you use. There's there are thousands of reports that you can look at, and we can talk about which ones you want to choose later. But in theory, it's somewhere between onshore and offshore wind. If you are a CCS advocate and you are trying to argue economics of CCS, one of the things that you will talk about is you will say that the grid connections are going to be much lower than renewables, and in general, those aren't covered in the cost currently. So you need one connection instead of 7 connections on the outside of Orkney. And normally, in the economics, those aren't covered. Also, if you're a CCS advocate, you will say something like, there's no value given to the dispatchability. So if you have a big energy system with lots of intermittent things that you can't control, something that you can't control should be more valuable. And that value is just never really covered in the economics. But on the other side, you can be a CCS critic, and you can say that the cost of this technology goes up the less frequently you use it. So if you're going to have this plant that is only going to turn on when the wind is down, that means it only turns on maybe half the year, 1/4 of the year, and that makes it really, really expensive. But regardless of whether you are a critic or an advocate, everybody sort of generally agrees that it's a valuable tool set to have in a low-carbon system. It's so much cheaper to achieve your goals using this tool in some way, shape, or form than it is to not use it at all. Okay, so what do we do at the University of Edinburgh? So we can kind of break it down into academic research on carbon capture and storage technologies, and then networks and industrial research. So and within the School of Engineering, we do a lot of post-combustion capture work, and this is a very gross generalization, but if you're lazy, you can think about the near-term post-combustion technologies, so like how we do it now and how we'll do it for probably the next 10 years, are sort of captured within the IES division, so that's Matthew LeCue and Hannah Chalmers. And then medium to long-term technologies, so how you're going to do it 15 years from now, are sort of done within IMP. And then we do a whole bunch of CO2 storage work, which is not necessarily within the School of Engineering, but there's a big division that does it within the School of Geosciences. And then in addition, we do CO2 transport, so you have these big streams that need to go places, and that is shared between engineering and geosciences. But that's only one half of what happens here. The other half is kind of networks and industrial research. So we have 2 networks that kind of link academic work, industry, and policy. The first one is this thing called the UK Carbon Capture Research Centre, and all of the branding and things are up here, which you can kind of see. And the reason that is because they sponsor a good portion of my research. If you have no idea where they are, they sit on the ground floor of Sanderson. So you can kind of see them, and Steph is right there. So they have a whole secretariat, which I don't think IES is very well aware of. And then so that's for the UK, and then there's also a Scottish carbon capture and storage network, which also exists, which also does some similar things and some different things. And they are also at the University of Edinburgh. Nominally, they're located at the Carbon Innovation Centre, which is on Infirmary Street, but they're kind of scattered everywhere. And then, in addition to all of that, there's this whole building that nobody ever really remembers that sits on KB's campus, which is the British Geological Survey. They do lots of carbon CO2 storage work, and we just sort of forget that they're there.
They've moved it.
Yeah, now they're here. What? Okay, so that's what we do. So now, what was my project? So all good projects start with a really long acronym. My project's acronym was COMCAT, and it's this thing right here: Control, Optimization, Measurement of CO2 Absorber Transients. You don't need to know what that means. But the high-level research question was this. So if you have a fossil fuel plant with carbon capture fitted to it, that thing will exist in the same world of other low-carbon stuff. So you're going to have lots of renewables. You might have some nuclear. You're going to have electric vehicles and a smart grid and all kinds of wonderful things. So if they're all going to exist in the same world, the value that the carbon capture plant is going to give is by being dispatchable, by being controllable, by being able to fill in when the intermittent energy sources aren't going. So what are the implications of doing all of that at the carbon capture plant level? So that was sort of my research question. And what we did was we kind of made a collaboration. So it's an industrial collaboration thing. So here's Edinburgh here, that's us. Over here is this company called Doosan Power Systems. They make boilers and compressors and gas turbines and all kinds of wonderful things. So they are a fossil fuel plant original equipment manufacturer. And then we also had SSE, which is the utility that we all sort of know. They sort of exist everywhere, but I put them in Perth. And then we have Vattenfall, which is actually a Swedish utility, but the people that we worked with were from Amsterdam, so I put them here. So this is sort of the group that I worked with. And then the plan was to, whatever work I did, needed to go to this fancy pilot carbon capture plant here. This thing was called CC Pilot 100 Plus. It lived in West Yorkshire at the Ferrybridge Power Station. And then there's me in front of a very large piece of equipment. I advise all of you, whenever possible, to get pictures in front of very large pieces of equipment. All the cool kids do it. You've seen Duncan do it. You should make sure that you get pictures in front of big things. Okay, so it was also sponsored by the Energy Technology Partnership, and these are the people. So, again, it has to do with control, optimization, and measurement of post-combustion systems. So here's a picture of one. I can do it with the mouse here. Here's a picture of one. Basically, it's a continuous gas-liquid mass transfer process, if you think about it in terms of chemical engineering. You have this flue gas, which comes in from stuff that was burned. It gets cooled down, and then the CO2 in that gas stream, we want to get out. So you grab it with typically an aqueous amine solvent. It has to have some kind of amine functionality, which is the NH2, if you don't like chemistry. And that will selectively absorb CO2 from your gas stream, and it won't absorb anything else, usually. That solvent will grab all the CO2 out of your gas stream. The gas stream will leave with less CO2 in it, so you've captured carbon. Then that solvent is now full of CO2, and you need to get it out. So you move it over to this other vessel, which is called a stripper, and then you heat it up, and then heating up makes all the CO2 leave the solvent. So then that CO2 leaves out the top. You can compress it. It's very pure, et cetera, et cetera. And in order to do that, you need to have steam come in, which you will typically grab from your power generation cycle. So we've burned stuff. We're going to use that steam to make electricity. Now we use some of it to regenerate. So if you think in terms of a chemical engineer and you think about what is controlled and whatever, so if you look at the process inputs here, you're going to have a flue gas. It's going to have a flow rate and a composition, so it's going to have lots of CO2 or small amounts of CO2 depending on what fuel you burn. And then you have steam coming in to do the regeneration. So that's going to have a given flow rate and a given temperature and pressure, depending on where you extract it from in the process. And then you have process control objectives, which are you want to achieve a certain capture level. So if you have this amount of CO2 coming in, you want to get 90% of it, or 99%, or 85%, or whatever. So you kind of choose how much CO2 you want to grab. And then you also want to make sure that the CO2 is correctly pure, because you have to compress it and send it down a pipe. And it has to be above a certain purity to do that. So that's the process inputs and how you kind of control it. And then if you want to optimize this whole thing, because you don't really want to control things, you want to do it in the most efficient way. The way you sort of optimize is, it's called energy efficiency. So you want to make sure that you do this for the least amount of energy required. And this is sort of a tricky calculation to do, but basically all the stuff that you've input into your process, you sort of need to think about what that would have done to make electricity, and then you sort of take that number, so that's kilowatt electric equivalent of whatever you've done, divided by ton of CO2 captured. So you want that to be as efficient as possible, because that will lower the costs. That's what everybody's trying to optimize. And then in order to do the optimization, what you need is you need to measure some stuff and control some stuff, and you need to kind of build models around how to do this. So what you need to do is you need to measure the solvent flow, so that's how fast the solvent goes around in the circle. You need to measure the stripper temperature and pressure, because that will show how much CO2 comes out of the solvent. And then you need to know the solvent composition, so that's how full the solvent is and how concentrated it is in the liquid. If you think about measurements in this process, all of those things are really easy to measure. Flow, temperature, pressure, very easy. We've done it for thousands of years. But the solvent composition is sort of hard to measure on the process. So what we did was we said that's going to be the research objective. It's going to be to develop a new method for measuring the solvent, and that's the amine concentration and the CO2 loading. You don't need to really know what those words are, but it's how full the solvent is and how concentrated it is. So you need to make a new method and then integrate that method into this process and make it better than state of the art. So we're talking about embedded industrial instrumentation and a new way of measuring stuff. That was the research goal. And then you were supposed to take that and put it onto the plant that existed in the previous slide. Okay, so at a super high level, how do you make something that's better than state of the art? Well, marketing people have already figured this out for you. So you can use these kind of buzzwords, like understand your customer's pain. So the customer's pain was, I need to measure this thing, and it's really annoying to do right now. Basically, we have to do a chemistry experiment currently, and it takes forever, and it's annoying. So we know what the customer's pain was. It was that the solvent analysis wasn't good enough. And then you kind of need to identify these things called key performance indicators. That's another marketing buzzword. So it's just, what are the traits that you want out of this thing? Then you take everything that exists today and evaluate it against these metrics. And then you basically have to make a technology that beats the metrics. It's quite simple, but hard to do in practice. So anyway, so you can do all of this, and I did, and you basically can make a wonderful little graph. So these key performance indicators for any measurement technique, it needs to be accurate, it needs to be robust, it needs to be versatile, it needs to be cheap, and it needs to be fast. This is how all industrial instrumentation works. It's fairly obvious. But you can sort of break these things down and make them a qualitative index or whatever. So I did that. So I took all of those key performance indicators and measured them against everything that exists today that you can buy, and some things that are also research methods. And I kind of came up with a graph. So you have this little graph here, and it basically says whether any of these indicators are good or bad. So poor, average, good, and very good. You can kind of just do this analysis. And so what you sort of find is that basically all of these things provide a reasonable amount of accuracy and precision, so they're precise enough, but they tend to lack measurement speed and robustness. So they break pretty easily and they take forever to do. And then some of the methods will become more specialized, so they'll sacrifice versatility to get better precision. So you sort of know that. And then some of these research methods look great. So this guy and this guy are both spectroscopy methods, which we don't have to get into. But they can do wonderful things. They can be very, very fast. In theory, they can be very, very cheap. But nobody knows if they're actually robust and ready for industry. So I basically treated these things as my competition and said, okay, well, I need to make a method that will be as good or better than this. So I basically had to think about it for a while, and I came up with this method that I'm calling inferential solvent analysis. I literally just made up that term. And the basic idea is you measure things that are easy to measure online. These would be physical properties, chemical properties, whatever. And then from the changes in them, you infer the changes in solvent composition. In order to do this, you just need to calibrate very carefully and kind of build some physical models. And then once you do all that, you kind of deploy it in a program and you can get this continuous data out. So I did that, and it's got a lot. So that kind of method has a lot of things going for it. The first thing is that you can do it continuously. So we've measured the speed KPI is great. You can also do it with cheap stuff. So the economics KPI is great. That's been industrially proven and really, really rugged. So the robust KPI is great. All in theory, just hasn't been proven. So the plan was to then lash together a bunch of kind of components, put them onto this little aluminum board here, and then deploy it at this capture plant. So you can kind of measure in real time these solvent composition things, and then you basically solve the industry's problem, everybody's happy, and they give you this pat on the back. So that was totally the plan. And we had done this, and we had deployed it at this carbon capture plant in 2013, and it was going to go great. There was lots of things going for it. I got to compare against wonderful state-of-the-art things. I got to do it on an industrially commercial solvent, but we had already kind of worked out all the IP. The lawyers were happy. We had figured out the safety. It was all great. We had paid for it. I had a great working relationship with everybody. It was going to be wonderful. Problem is that real timelines exist, and they kind of screw you up. So basically, by the time that I had created this sensor, put it on the aluminum plate, and put it at the plant, the test program had already moved on past the data that I needed that was useful. And I knew that ahead of time, and I was basically saying that's completely fine because there was this assumption that they were going to kind of come back around and do the whole thing over again with more accurate data to kind of be smarter, and I was just going to catch the whole thing on the second pass, assuming that we got extra funding. Everybody told me they were totally going to get extra funding. It wasn't going to be a big deal. Then they didn't get extra funding, and so the plant abruptly closed in 2013. And the lesson you can take from this is that it's really, really easy to blame somebody else for this problem, right? You can say, oh, the government doesn't support CCS, or people don't really understand how this is working, or the project management was bad. But in reality, that is completely on me. That was a huge technical risk that I had sort of known about and just didn't contingency plan for at all. So I sort of internalized that and understood that this was actually my problem rather than everybody else's. But it was a huge setback. So we're sitting there with this like half-filled data set that if you stared at it correctly, it would look like it was really promising, but you didn't have any real comparisons and you didn't have any proof. So you were kind of in trouble. But if you remember back at the very beginning, there were all these like industrial networks and stuff that were already at our school. Basically what happened was I got really lucky. And so you can kind of ask people for help, and we found other carbon capture plants that existed in the world, because that was the only one that was useful in the UK. That one shut down and there was nowhere else to go. So I had to kind of look outside. And at the University of Edinburgh, the CCS community is pretty small, and we are somewhere between really connected and ludicrously well connected. So I sort of just asked for help, and we found these other capture plants. So I've kind of expanded this map here that we were talking about before. So here's where we were, and then we found two people who wanted to try this out as well. So one of them was in Alabama. This is the Carbon Capture Research Center for all of the US, and then there was one in Switzerland. So that was great. So we now have these plants that we can try this out on again. And then I had to just scrape together a little bit of money, which I thought was going to be kind of scary, but actually was a lot easier than I thought. So you kind of just apply for travel grants or international grants that all the PhDs can get. And I also kind of latched on to an EPSRC grant. So I was able to go and do this, which saved me, basically. And then out of that, it was all wonderful because we had these follow-on collaborations and we have new projects and we kind of have continued on to do all of this work. So that's the wonderful story, but I do have to tell some battle stories a little bit here. So the first one is that if you see here, we live here, and then you go across the ocean and you go to the US. And it seems very, very straightforward, but the way that an academic UK institution and a US power plant think about safety, insurance, IP is completely different, just miles apart. And so basically they had to kind of figure out a way to let me go on site without suing each other, without giving away each other's secrets, figuring out who to pay who and how to do what. That was a huge problem. It almost fell apart like 3 or 4 times. And basically the only thing you can really do is try and become familiar with what the barriers are. That means like understanding insurance contracts and whatever, and being really, really nice to the people who do them. So I would highly advise any of you who are trying to do useful things to just be really, really nice to and patient with whoever is doing these kinds of admin things. Our contracts team is unbelievable. We just don't know it because we hand them the contract and they do it eventually and we think it takes forever. But they're unbelievable. The insurance team is unbelievable. The import-export people are great. And you just have to be patient and then you can do these wonderful things. So this thing was going to fall apart about 3 or 4 times over huge barriers that they eventually all kind of compromised on. The second thing that I'd like to tell a war story about is at this plant, because it had taken forever to get all of these contracts together, I had a 14-day trial. They told me this, 14 days. That was loads of time. I was ready. I planned it all out. I made my little Gantt chart, A, B, C, D, day 1, 2, 3, 4, 5, 6, 7, 8, whatever. That was great. I'm there. I'm plugging it in. On day 0, they tell you have a 6-day trial. And you only get to go on the plant for 3 days because it's a bank holiday on the Monday. So I could have been screwed again, but I had learned from my first lesson. I had kind of learned that, you don't know how long you're going to have, how do you prioritize getting what you need and getting out. So that actually didn't trip me up the second time, only the first time. But these kinds of things happen on real world. So anything that is a real world trial, your priority of doing great science is way below their priority of turning on off the plant. You should just know that. Okay, so anyway, if you do all of this, you can kind of distill all of this knowledge and data that I got into these little graphs. So here's one of the little graphs that you kind of can like put in a PhD and call it a day. So this is a comparison of the measurement outputs of my sensor versus the state of the art. So the little blue line and the little gold line are my continuous outputs. So you can see with time they just go on and on and on. And these little dots here are what the state of the art is. And you can say, you can really easily say, look, the line and the dots really match up and we're done. But there's a lot of other things kind of subtly going on here. The first one is that you can't get the dots nearly this fast. It just can't happen. So what they really did was they took a lot of samples and then like 3 days later analyzed them all in a row. So you can't really ever get the dots that fast. But the other thing that's going on is that I hadn't like made this fancy computer program yet. So basically I had done all of this data post-processed as well, kind of just compared to that. So we kind of had these two data sets, but neither of them were real time. But you can sit there and say, well, the results are promising and that the instrument didn't break. So you turned it on, you plugged it in, it didn't break. So you can say its robustness and speed are great and it's cheap. So in terms of these KPIs that I'm talking about, this is really good. If you do some statistical analysis on these trends, you compare the dot with the line over and over and over again, you can kind of come up with these uncertainties here. So how close are the comparisons over a whole data set? And so you get these numbers here. So the number you can sort of say is that so one standard deviation out, you're about 5% relative the comparison. Now that means nothing to you until you know how good the dot is. So the dot, its total uncertainty is about 5 to 7% relative. So if your difference is 6% relative and that thing's uncertainty is 7% relative, you're really not adding a whole lot of uncertainty there. It's already kind of baked in. So that's kind of a useful thing to say that you may not significantly add to the measurement uncertainty by doing this. And then if you did all of this and made a program and plugged it in and gave it to the operator, you can say that he gets better information faster. He can make better control decisions and save lots of money. We kind of proved this in the Switzerland trial, which I'm not going to talk about because one of our colleagues might present on this later. You can also do really effective and clever dynamic control. And there's papers about it that we can show you if you want. Okay, so since I've been sitting up here, I have to do a technical rant. I'm going on like to a side point. And it has to do with the display of measurement comparisons. If I have a measurement and I want to compare it to my model, or if I have two measurements and I want to compare them together, or whatever, very often I see this thing. So it's here's my measurements, here's what the expected was, I draw a y equals x line, and they fit really close to the line. Then I'm in Excel, and I'm lazy, and I right click, and I say, look, here's the r squared, it's really close to 1, I'm done. That is not useful at all. So basically, this is a very common practice, but it doesn't give you any information at all about the nature of the comparison. The other thing it does is it basically neglects all of the uncertainties. So that red line, those red dots, they all have uncertainty in them. And you're just kind of ignoring that. Also, your black line may also have uncertainty in it. And you're just ignoring that too. So this air and noise of repeatedly comparing things together, you just ignore it all. And it's pretty bad practice. So what I would encourage you to do is read this paper. It's called Bland-Altman. You can Google it, and basically it's from the Lancet from 1986. It's got 32,000 sightings, and they named a plot after it. Okay? So what you're doing in the Bland-Altman plot is you're basically taking this y-x axis and tilting it 45 degrees and making that the x-axis. Okay? So I'll show you what that means. So basically what you're doing here is I tilt this and make the 0. So there is no difference between the comparisons on the y, and then on the x is what I've measured. Okay? And you can read the paper, and you should read it about 2 or 3 times, but it's wonderful. And you can do a lot of really clever things. So one of the clever things it can do is it can actually quantify for you the added uncertainty for if you take a measurement and you go against the calibration. So like you have this calibrated set, and you've now take this new measurement that you have and compare them. this thing can actually quantify the added uncertainty for you. So what it does here is I have this comparison. I know the uncertainty of one of the measurement sets, and the other one is a new one. So if you do all these comparisons, blah, 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 you can see that on average, the difference between them is 0. That's good. That means that it's random noise that we're talking about here. And then you can see how often, what the distribution of the scatter is, add together the uncertainty, and you kind of have this new quantification. That's one of the things you can do. The other thing you can do is you can kind of try and qualitatively assess measurement bias and measurement offsetting, and you can't really do that very easily here. So if you have this comparison, you want to make it better, one of the things you can do is you can look and see if there's a bias in your model, in your measurement, and what does that mean? How do you make it better? So you can do that here, and for this one, I'm seeing this random slope here. Well, why is that? So you can look back at your model and refine it, or you can just kind of fudge factor to make the comparison better if you feel like it. But you have this really quantifiable way to do it. So anyway, that's the Bland-Altman plot. Please start using it whenever possible. Okay, so basically this graph back here allowed me to finish my PhD with a couple other things, but basically that was it. The instrument didn't break, its accuracy and precision are pretty close, and it's cheap. So that's a novel contribution. Okay, so that was done. Acceptable accuracy, robust, fast, and relatively low cost. And if you do it at the plant, you get industrial proving to a degree. So what do you do next? So that was mid-2015. We are a year on from now. So the new opportunities are quite exciting. So when you do this kind of industrial proving at research centers, they talk about it. And so when they talk about it, eventually the network kind of gets back to you. So we've been approached by so carbon capture isn't really a well-developed industry. There are 2 commercial players that have built post-combustion capture plants. The good news is that both of them are interested in trying out my sensor. So it's not a big market, but I am going to be demonstrating to the two people that are there. So I brought up the map again, and so we've added red dots. Industry leading, because there's only 2. So one is called Shell CanSolve. So we all know well that Shell, they exist here in Canada. And then the other one is Mitsubishi Hitachi Power Systems. So these guys made the first carbon capture plant ever. It's in Boundary Dam. We can talk about it later if you want. And these guys are making the second one ever. It's going to be in Texas. So I basically get to plug my sensor in and do a commercial demo of it to these 2 people who might be interested in buying it one day. So you need to kind of do more work. I need to make it real time, and I need to kind of get the programming right and blah, 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 and redesign the sensor. But in theory, you do that by fall of this year. And the EPSRC and the UK CCSRC were nice enough to provide me with funding to do that. So I got this thing called an Impact Acceleration Grant and some travel funding to try this out. So I get the chance to kind of redesign it and maybe make it into a commercial system. Okay, so there's all that. But now I want to kind of zoom out. And basically, in the last 3 weeks or so, I've been kind of looking at professional development because I'm on this IES PGRA committee, and that was what my job was. So I'm trying to make our professional development training better for all of you. And so what that means to me right now is all I'm trying to do is trying to digest the human resources jargon, which is really hard to do. But one of the things that they talk about a lot are these things called competencies. So that's stuff that you do, what you're good at. And you can kind of break them down to technical and behavioral competencies. And the reason I'm doing this is because there's lots of technical things that you learn during your PhD. And we're technical people, so we tend to talk about them a lot and list them. So you can just kind of go over and over and over again and put all these wonderful technical things down. And you can just list them forever. Okay? So these are all things that I've learned. I'm very happy that I've learned them. But anybody can learn this stuff, right? Any engineer learns these things. This isn't what makes you special as a PhD. What makes you special as a PhD are the behavioral competencies. So some of the things that I think we're good at learning are like networking and collaboration. I've talked a lot about like there's this network that sits next to me in this school, and it's kind of done wonderful things for me. We all need to have networking and collaboration skills because the way you increase your impact is by telling other people what you do and like multiplying the effort. So that's really important. Mastering new technical knowledge. I didn't know any of these before. I know all of these now. That's valuable to that makes you special as a PhD. Creativity, design, and prototyping. Every PhD needs to make a novel contribution to science. And very typically that's like a bespoke model that gives you a great graph or this one-off experiment. You're very blessed here, though, that you have these 3 or 4 or whatever years to just do whatever you want and kind of answer the question in the best way that you feel. So I'm telling you right now, the difference between your bespoke computer model and like an industry tool is just a little bit of computer code to integrate. And the difference between your experiment and an actual like product that can exist is like more robust design. And you have the time to do that. So try to if you can. And then effective communication. You need to understand you're doing really technical things. You need to tell people at all levels, whether they're smarter than you or not, or whether they're interested or not, what you're doing. And then resilience. So basically you're going to be told no a lot, you're going to fail a lot, and you need to get back up. And so you need to come up with everybody needs to come up with their own personal reason to get back up. But we can all take solace in the fact that it's happened to everybody else in this room. Okay, so those are things that we're good at, right? But what happened to me are, I've sort of stepped back and think about the behavioral competencies I almost learned or needed to learn that you should learn maybe. So this is like, try and do this because I didn't. So the first one is awareness and agility with relation to the commercial landscape and the research landscape. Your PhD is ideally 3 years long, but probably more. Okay? So that's a project that was written 3 years ago. And it wasn't written 3 years ago. That was when it was granted. It was probably written a year or 6 months before that. And then by the time you're done, that's like 4 or 5 years that you've been working on this one thing. The world moves on. And the best technologists and sure as heck the best researchers in this world work on completely different things than they did 5 years ago. So you should try and be aware of that, and you might have to adjust your research question a little bit halfway through to make it relevant again. Just know that. The other thing is that I think that we're really bad at is project management and especially contingency planning. So we all make these wonderful Gantt charts because we have to, and it's all chronological. I do this, and I do that, and I do that, and I do that, and the end is always the ideal end, right? So I know that when the project is a complete success, it will happen on month 18. But we aren't really good at doing contingency planning. What if your entire experiment is garbage, right? What do you do then? And what if this thing that you're waiting on takes another 6 months or whatever? We tend to not plan that way. We don't plan stochastically. Is there a chance that it's going to go wrong? We don't do that. We plan kind of chronologically. And it trips us up a lot. It makes a lot of us extend our PhDs. The other thing that I didn't really do at first, and I don't think a lot of us do, is applying our technical skills to non-technical problems. Right? Like I had to know, so right here is a technical competency. Functional knowledge of IP, contract, insurance, and import-export laws. I'm not a lawyer, but I had to know that. And I had to know that because if I didn't, the project would fail. There's going to be things like that is going to happen to you. Things that are outside of the sphere of engineering that you still need to apply your problem-solving skills to. And you're just reluctant to do it because that's not what the label of your training is. But you're probably going to have to do that. Taking ownership of your project. So very, very quickly you need to realize that your advisor, it's not your advisor's project. It's not your advisor telling you what to do. You need to take ownership of every single thing that happens. So all of these uncertainties that you have about, the workshop didn't get back to me, or, I don't really know if I'm allowed to go to this conference and my advisor didn't tell me, or the purchasing order hasn't gone through yet, or I might get time on this machine 3 weeks from now, but they weren't really sure. Those are all uncertainties that can screw your project up. So you have to, 1, plan for them, and 2, kind of interact with people to lower the uncertainty. Am I really going to get on that machine or not? And we just don't do that. We're kind of timid because we're worried what the advisor would say or if we're going to upset people. But nobody cares about this project nearly as much as you do. And you have to kind of take ownership of it. And then the last thing that we're really all really bad at, I don't know, that I was really bad at and I've never mastered, is the ability to deliver a functional and imperfect output on time or early. Inherently, we're sort of perfectionists, and we just want this thing that we've been working on forever to be perfect. and we just carry it on, refining it, and we can't even fathom delivering it half done and horrendous in our mind and early. We just can't, I don't know, I couldn't do that. And it cost me at the end of my PhD. I had to extend it and whatever and all this kind of stuff. So we're really bad at this. And this has to do with this contingency planning. But basically you have to think in your head, what does it take to make this really ugly output? What's the bare minimum? And then deliver that first and then kind of build on it. It just changes the way you have to plan. Anyway, that's the rant over. Okay, so I'm finished. And I'm happy to take anybody's questions. Thank you.
This production is brought to you by the University of Edinburgh.